All right, I'm going to take a look at FRQ number 1 from AP Prep sheet. They want me to find the area of this region, and notice we have that sine of pi x function at the top, and the lower function is y equals x cubed minus 4x, so you do have to kind of be able to pick out which is which. So remember, when you're finding an area, you're really adding up the areas of rectangles moving from side to side. And so Forrester always has this kind of drawing these little strips here. And notice the x-coordinates are the same, so we can call this x, y2. We can call this point down here x, y1, maybe something kind of like that. And a dA statement, that would be the change in the area as you move from left to right from one rectangle to the next. Area of a rectangle, of course, is a length times a width. If we fill that in, the width here, notice, is a little horizontal change. That's going to be a dx. And the length, of course, is going to be y2 minus y1. So dA is going to be equal to y2 minus y1 times dx. And, of course, that really is just going to be the sine of pi x minus the x cubed minus 4x. Make sure you've got parentheses on both of those so that your y2 function is this upper sine function, the y1 function is that lower cubic function. And then you're multiplying by dx, and you're taking the integral of that. The integral, we're starting, this is all in terms of x, so we're starting at an x value of 0, ending at an x value of 2. It's going to look something kind of like that. Let's take a look at the answer on this one and see. Now, they did run this on a calculator, but you can see there, same answer that I got, and we already have 3 out of 9 points, which is pretty nice. Okay, let's move on to part 2. Part 2 says the horizontal line y equals 2 and y equals negative 2 splits the region into 2 parts. Write an integral expression for the area of the part below that horizontal line. Okay, so I'm going to draw that horizontal line down to here. It probably wouldn't really be that low, but there's y equals negative 2. Okay, we need the intersection points here and here, okay, because that's where our integral is going to start and end. And anyway, same kind of thing here. We're finding areas, so you can have your little rectangle here, and actually, let me do my rectangle over here. You got your little rectangles here that you're adding up from left to right. I'm going to call this the point x, comma. We know the y-coordinate there. The y-coordinate's negative 2. Same x-coordinate down here, and I'm going to call that a y1. Okay, so same kind of thing. You're going to write your dA statement. The area of one of those strips is a length times a width. The width, of course, is still a dx. I'm kind of surprised they gave us one that sets up almost the same way. Notice the length here. It's the upper, see if we can focus on that. It's the upper y of negative 2 minus the lower y of y1. So negative 2 minus y1, okay? And that's going to be our equation. We're going to take the integral of this starting from the beginning point there, ending at the ending point. We're going to need to set negative 2 equal to that lower function, which is the x cubed minus 4x function. And it might be a whole number of values, but I bet because it's a calculator problem, you'd probably solve it. So you could graph y equals negative 2 and x cubed minus 4x and see where they intersect, or you could move the 2 over and use the 0 function and figure out the intersection points. We'll look at those in just a minute. Anyway, we put all this together. It's going to be an integral that starts here and ends there, whatever those values are. We're going to have negative 2 minus function x cubed minus 4x. And you don't really need to simplify it. So negative 2 minus that, all of that times dx, and then our bounds. Let's go take a look at the solution on this one. Okay, negative 2 minus x cubed minus 4x. They found the intersection points there to be at 0.539 and about 1.675. Okay, they used variables to represent those in theirs. And we're already up to 5 out of 9, which is already a passing rate, which is pretty nice. Okay, let's take a look at part C here. All right, part C, the region R is the base of a solid. Each cross-section perpendicular to the x-axis is a square. They want the volume of that solid. So I may have to sketch a new picture here, but we can do that. So it does this sort of thing. It's going like that, and it kind of cuts down like this. Okay, so each cross-section perpendicular to the axis is a square. Okay, so perpendicular to the x-axis, we're looking like this. And so we have these little square projections, and you basically need to show these kind of, angling out like this, maybe that sort of thing. It's got a little bit of a width. And, maybe your squares look something like that. You're going to have very small squares down here. You're going to get very large, very tall squares as you go farther over. And we just kind of continue that until you get down to the end. But let's look at this one right here. The same kind of thing here. You need instead of a dA statement, you need a dV statement. We're going to be adding up the volume of these things. The volume of one of these little square slices, remember it's a square, so we could maybe say it's got a width of W and the square is maybe an S by S. We could say the volume of one of those slices is S squared W. Okay, so we just need to find one of the sides in terms of our variables. The same kind of thing, put points on the curve between the two different curves. We've got the same X coordinate, and maybe we'll call that a Y2. We've got a same X coordinate down here, maybe call that a Y1. So the length of that side is the upper value minus the lower value. That's Y2 minus Y1. So that's the length of a side, is Y2 minus Y1. The width here, if you notice, is a little horizontal change. So that's going to be a dx, telling me everything needs to be written in terms of x. Okay, so we could go ahead and fill all that in. I'm going to take the integral starting at 0, ending at 2, x value of 0 over to an x value of 2. We're taking the y2 function, which is the upper function, that's sine of pi x, and we're subtracting the y1 function, which is the x cubed minus 4x. Make sure you've got parentheses on this. Okay, so it's the side squared times dx, and everything is in terms of x now. That should be our integral there. And let's go take a look here. We're already at a really high rate on this problem. Okay, and you can see there, we did get the right answer. They want you to stick it in a calculator. We'd be up to 7. Okay, last part of this problem is really tough. I've only seen it come up once, but it's a good thing to think about. It says this is modeling a pond, okay, and they're saying that the depth of the water is given by 3 minus x. So in other words, if you wanted the depth like right here when x is equal to 1, the depth 3 minus 1 is 2 feet deep. If you wanted the depth here, 3 minus 2 is 1 foot deep. If you wanted the depth here, 3 minus 0 is 3 feet deep. So basically it's 3 feet deep here, gets to 2 feet deep, and then over here gets to 1 foot deep. And we want to find the volume of that water in the pond. And on the surface, that sounds really terrible, but this really can be done almost exactly the same as the last problem. We can really just use slices here and do more or less the same kind of thing that we had previously. Let's see if I can get this picture drawn again. The picture's getting worse every time I draw it. Okay, well, there's my function. Okay, so basically, I can just do slices all the way across and just add up the volume of the whole thing, but the volume formula is going to change. So let's do one of my slices across here. So I've got basically a slice. Now the depth, these are not necessarily square slices. Okay, I'm not drawing this very well. Let's scratch that. Let's go over here. Okay, so the depth is changing at different places, and that's where this gets a little bit dicier. Okay, but we still have these kind of rectangular slices here, and this should really be dipping below the pond, but I can't do that, so I'm going to have it project up and out as opposed to going below the pond, but you get the idea. So the volume of one of those slices, you could say it's a length times a width times a height. Okay, the width of this thing is a little horizontal change. That's just a dx. Okay, the width of it, you've got a point x, y2, you've got a point x, y1. The x coordinates are the same. The width of that is going to be y2 minus y1, upper value minus the lower value. Okay, so y2 minus y1. The length of it, or the depth of it, is what I'm doing here. That depth there is defined by that h of x function. Okay, so I'm just going to put the h of x function in here, and that's going to give me the depth of each of these things. And, it'll give me one depth here, and it'll give me one depth over here, and give me another depth over here, and that's totally fine. The integral will take all this into account. So same thing, we're taking the integral from 0 to 2. The h of x function is 3 minus x. I'm going to replace that. y2 minus y1 is going to be sine of pi x minus x cubed minus 4x, okay? And then it's all times dx. And I think that integral should end up doing it. Let's go back and let's take a look at their answer and see if that's the same thing. And yeah, they ran it through the calculator, but same answer. So interesting problem, but not terrible. All the parts kind of link together.